Alright, let's talk about something big. I mean, really big. We drive over them every day without a second thought. But have you ever stopped to wonder how a massive bridge gets built? How do we span miles of open water or a deep valley, laying down a ribbon of concrete and steel, cars, trucks, trains? It's not magic, though sometimes it looks like it. It's a job. Tough, dirty, and incredibly precise that takes years of planning an army of skilled workers and some of the biggest machines on the planet. This isn't just about connecting point A to point B, it's about conquering a piece of the landscape. Today we're going behind the scenes. We're going to peel back the layers and look at the hard work that goes into creating one of these modern marvels. The goal isn't just to build a bridge, the goal is to build a lifeline. Shrink distances, connect communities. Every great bridge starts with a question: how do we get from here to there? But the real work begins with the answers. Engineers, city planners, environmental scientists. They have to figure out the best possible path for the bridge. This isn't just about drawing a straight line. They study traffic patterns. They analyze geological surveys, weather data, tide charts, shipping lanes. Once they have a general idea, the surveyors head out to the site. These are the folks who take the guesswork out of the equation. GPS laser scanners, sonar for underwater mapping. They create a precise digital model of the terrain. They take core samples from the soil, drilling deep into the earth and riverbed. Close-up of the soil cores. Soft clay? Solid bedrock? A mix of sand and gravel? The answer to that question determines everything about the foundation. It's meticulous, often muddy work, but without this data, you're just building on a prayer. With all that data in hand, it's time to choose the right tool for the job. A suspension bridge or a cable-stayed bridge. A suspension bridge, like the Golden Gate, uses massive main cables draped over tall towers to hold up the road deck. A cable-stayed bridge has cables running directly from the towers to the deck in a fan-like pattern. The choice depends on span length, the ground conditions. With permits approved and blueprints finalized, the real dirty work can begin. The first order of business is to prepare the work site, a massive undertaking. Crews build access roads for heavy machinery. Temporary offices are set up. Storage yards for materials are arranged. Workshops for fabricating parts are built. For bridges over water, crews build a temporary pier or trestle out into the river. The site becomes a small, self-sufficient city, buzzing with activity. Safety protocols are drilled from day one. This is a dangerous environment. No room for mistakes. Now we go deep. The foundation is the most critical part of the bridge, and it's completely hidden once the job is done. The goal: transfer the immense weight down to solid bedrock or stable soil deep underground. For piers in the water, that often means building a cofferdam. A cofferdam is a temporary, watertight enclosure made of interlocking steel sheets driven into the riverbed. Once the cofferdam is set, water is pumped out, creating a relatively dry, open pit on the river floor. It's mucky and challenging, but workers can excavate as if on dry land. Next, crews sink piles. These are long, thick columns of reinforced concrete, or steel piles. A pile driver hammers these columns down, one after another. They go until they hit a layer that won't budge, refusal. For main towers, we use huge foundations called caissons. A caisson is a giant hollow concrete box sunk through water and mud. With the foundations firmly set deep in the earth, the bridge finally starts to grow upward. The first visible parts are the piers. The main towers appear next. Piers are the shorter support columns that hold up the approach spans. Towers are the giants that handle the main span over the water. Both are usually reinforced concrete. It all starts with building a form, a temporary mold for the concrete. Complex steel form structures are assembled, then raised after each section is poured and cured. Workers assemble a steel rebar cage section, then clamp formwork around the rebar. Concrete is pumped from below. Concrete is also lifted by cranes in massive buckets and poured. The mix is carefully controlled for strength and durability. After pouring, the concrete must cure, harden over several days. Surfaces are covered and kept moist during curing. The sequence repeats, weighing layer by layer as the pier or tower climbs. For cable-stayed towers, builders often use slip forming. For suspension tower construction, slip forming is also common. A slip form is a single ring of formwork that creeps upward pulled by hydraulic jacks. Concrete is poured at the top as the form moves, and the hardened tower emerges below. The result is a seamless, joint-free tower and much faster progress. Crews work around the clock in shifts to keep the slip form moving, sometimes only inches per hour. Taller towers mean higher risk and complexity. Workers wear safety harnesses and tie off every tool. Cranes are extended or mounted on the growing tower itself. Engineers check alignment with laser instruments and with GPS receivers. Even tiny errors below can mean feet of offset at the top. This vertical climb creates the bridge's iconic silhouette and gives it the strength to carry immense loads. Once the towers stand tall, the real magic begins. Spanning the gap between them. This part of the bridge, the superstructure, is the road deck and its supporting system. How it's built depends entirely on the type of bridge. For a suspension bridge, the first step is to string the main cables. A single pilot line is pulled from one anchorage over the tops of the towers to the other anchorage. That line pulls heavier and heavier cables across until a temporary catwalk, the footbridge, can be built. Workers spend months on this catwalk, high above the water, spinning the main cables. A spinning wheel travels back and forth along the catwalk, pulling a single loop of high-strength steel wire with it. This repeats thousands of times. For a major bridge, each main cable can be over 15,000 individual wires, all bundled and compacted into one perfectly round cable that can be 3 feet thick. Once the main cables are complete, vertical suspender ropes are hung from them, the ropes that will hold up the road deck. It's modern engineering with a technique that's over a century old. For a cable-stayed bridge, the process is different. In stages, the deck is built outward from the towers, section by section, the balanced cantilever method. A huge crane on the deck lifts a prefabricated segment into place. Stays are run from the top of the tower down to the edge of that segment and tensioned. The crane lifts a segment on the opposite side to balance the load. The deck grows from both sides like a pair of wings. Stay cables are added in a fan-like pattern, each one tensioned for its segment. It's a slow, deliberate dance of steel and concrete, a few feet at a time. Eventually, the two cantilevered sections meet in the middle. The final closure segment is measured and lifted into place, connecting the halves into a single continuous bridge for the first time. It's a milestone moment for any bridge project. With the main structure spanning the gap, the bridge starts to look like a bridge, but it's still just a skeleton of concrete. The next job is to turn it into a functional roadway. If the deck was built in segments, the first step is to connect them all seamlessly. Workers weld steel plates. Workers pour high-strength concrete in the joints between sections. This makes the deck a single, monolithic slab. This ensures that the load from a vehicle is distributed smoothly across the structure instead of stressing one segment at a time. It's detailed work that requires precision and a steady hand, especially when you're hundreds of feet in the air. Once the structural deck is unified, the paving crews move in. First, a waterproof membrane is often applied to the concrete deck. On top of this membrane, several layers of specially formulated asphalt are laid down by paving machines. Paving machine laying base layer, paving machine laying top final layer, and workers smoothing edges. The asphalt is durable, flexible for temperature changes, and skid resistant. While the road surface is being laid, other crews install hardware, expansion joints, metal expansion joint, metal teeth, rubber expansion joint, rubber gap, steel barriers installed along the edges, concrete barriers installed in the median. Sidewalks are formed, bike lanes are formed, scuppers and drainage grates installed along the deck edges, light poles are erected, and electrical conduits run beneath the deck. Signage is mounted to direct traffic. Final checks. Workers tighten bolts and inspect fixtures. This phase transforms the raw structure into a safe, smooth, and fully functional piece of public infrastructure.